Hi, I'm Armand, representing Group 2, and we're doing a presentation on Chapter 10. Chapter 10 includes the area under a curve, the arc length of a curve, and the surface area of a curve. It also includes conic sections, and includes polar functions and cycloids. We will begin with Kyle explaining the area under a curve.
Alright, first we're going to be looking at the area under a function, the arc length of a function, and the surface area when a piece of a function is rotated around some given axis, first in rectangular form. So, if we're given some generic rectangular function like this, and we want to find the area under this function from A to B, let's say, we can approximate that area by adding up lots of little rectangles, where the area of a rectangle is the base times the height. The height is just the value of the function, y, or f of x, and the base is a tiny change in x, or dx. So we can sum up with an integral these rectangles, which are height, y, times base, dx. That's really simple. You just evaluate this integral from a to b, and that will give you the area under this function. For the arc length of the function, we have to look at a little triangle that's over the function here. So if we look at that, zoomed in, the height is a little change in y with respect to x, or dy dx, and the base is a little change in x with respect to x, or dx dx. Then the diagonal of the triangle by the Pythagorean theorem is simply the square root of dx dx squared plus dy dx squared. Dx dx is just 1. So this becomes the square root of 1 plus dy dx squared. And that is some little arc length piece of the function. If we integrate this formula from a to b, you can get the arc length of the function from a to b. So the surface area in rectangular form, if we have our generic rectangular function, y equals f of x, if we want to revolve it around the x-axis and see what's this surface, the wavy surface area of that as it is moving, then we're going to use the circumferences of little circles that are going around here, thickened up by the arc length of the function. And if we add all those up with an integral, we will get the surface area. So the circumference of one of these circles is 2 pi r, but r is the height of the function y. So we can just write y instead of r. The thickness is dx. But we also have to add the arc length into there, so not quite time for dx yet. We've got to have the arc length, which we found out before was square root of 1 plus y prime squared. Now we have our dx, and this integral from a to b, we want to find the arc length from a to b, then this will give the surface area of this function rotated around the x-axis. So next we're going to be looking at parametric equations, where instead of y equals f of x, it's y of t and x of t, where t is the parameter. So if we're given some generic parametric equation, y of t and x of t, if we want to look at the area under this function from a to b, it's almost the same process as in rectangular coordinates, where we're going to sum up with an integral a lot of little rectangles, where the height of the rectangle is the height of the function, which is very nicely given by y of t, and the base, though, is dx. It's a little change in x. But we can't just integrate this y of t with respect to x. So what we're going to do is multiply by 1 in a very clever way, dt over dt. See, all we've done is multiply by 1, but now this is the derivative of x of t with respect to t, and now this dt is what we're going to be integrating this whole thing with respect to. So this is the area under a parametric curve. If we want to look at the arc length of the curve, again, it's pretty much even easier than in rectangular form. We've got a little piece of the arc length, which is this, it's approximately a straight line if we zoom in a lot. The height of this triangle is a little change in y with respect to t. The base is a little change in x with respect to t. And this line that's approximating the arc length is just the square root of the sum of the squares of these things. So it is dx dt squared plus dy dt squared. So if we get that square root, I'll just write it as x dot, as representing the dot means the derivative with respect to t, just like prime means derivatives with respect to x. So x dot squared plus y dot squared. And if we just sum all these pieces up with respect to t, that will give the arc length of parametric function. Very simple. Surface area in parametric form is going to be almost the same as the arc length in rectangular form. We've got our generic parametric function, which is y of t and x of t. It's going to be basically the same process where we're going to be summing up a lot of circumferences of circles thickened up by the arc length of the function. So we're summing up with an integral from a to b, that's where we want to read the region in which we want to find the arc length, of 2 pi r. R is the height of the function, which is y of t. Y of t. The arc length is the thickness, the tiny change in the arc length, which we already saw was x dot squared plus y dot squared. And now dt, this integral will give the surface area of any parametric function rotated around the x-axis. All right, now we're going to be looking at the polar functions, which are pretty clearly the hardest to understand out of these three systems because they're not the nice rectangular square coordinates that we all know and love and have learned since basic algebra. Now there's all curvy and weird stuff, so it's going to be harder. But have to do it anyway because in calculus we have to do hard things. So a polar function is all where the radius depends on the angle that you've gone up from the polar axis, which is down here. This will be r of theta. The radius depends on theta. I'll write up here that x equals r cosine of theta and that y equals r sine of theta. These will be important to know for later. So the area inside of a polar function, we want to go from not a to b, but from theta 1 to theta 2. Got to write weird limits now. We can't use rectangles because, I mean, how do you get rectangles under this? It doesn't make sense. So we're going to have to approximate it by using little sectors of a circle, which will, because this, if you look at it really closely, actually, it's almost like a little isosceles triangle in here if you zoom in on this really far. So we're going to be summing up these little triangles where the area is 1/2 base times height. The height is the radius r. And the base is this little sector, which is r d theta. D theta is this little distance over here. So it's r d theta. That other r makes this an r squared, and the d theta becomes our limit of integration. This, well, you can pull the 1/2, I guess, outside if you want. 1/2 integral from theta 1 to theta 2 of r squared d theta. This will give the area inside of a polar function. The arc length of a polar function is much trickier and it's very messy, but so let's look at that. We've got our function here. We're going to start with the arc length that we know, which is actually going to be from parametric form. So we remember that that is dx dt squared plus dy dt squared. But now, if we use these, and we can let t be equal to theta for our purposes here. So these, we're going to use this, insert these into here, so we're going to take the derivatives of this, take the derivatives of that, square it, put it all under the square root, sum it up, and put a d theta after it if we want, and we can let that be our integral. So let's get started on that. The derivative of r cosine theta is r prime cosine of theta minus r sine of theta. That's just the product rule on that, multiplying these derivatives. That is x prime. The derivative of y, which is r sine of theta with respect to theta, that's going to be r prime sine of theta plus r cosine of theta. Again, just use the product rule on this to expand it out into this. Now we need to square these and put them under a square root. So this squared is going to be, I'll put this over here, r prime squared cosine squared theta minus 2 r prime cosine theta sine theta plus, I'm going to write that up here, plus r squared sine squared theta. That is this whole thing squared. Squared equals this. This squared is very much similar. We want to square all this. That equals r prime squared sine squared theta plus 2 r prime cosine theta sine theta, and then plus r squared cosine squared of theta. Now these, we're going to add these up and put them under a square root. These are exact opposites, so they cancel out, they give 0. These, r squared sine theta and r squared cosine theta, is just r squared, because we all know that sine squared plus cosine squared is 1. So this is just r squared over here. This, by similar logic, is just r prime squared. R prime squared. And remember, all this is under a square root, so here. This is a tiny piece of the arc length of a polar function. So if we sum up all the tiny pieces of the arc length from whatever angle to whatever other angle with respect to theta, this will give the arc length of a polar function after a lot of algebra from the arc length of a parametric function. Now, the surface area of a polar function when it's revolved around an axis is also pretty complicated, but we can get started on that. Let's see. So again, we can start with the parametric form using these and get the polar form. It's actually not too bad. So if you remember, the parametric form is 2 pi r squared, whether r is the height in this direction or in this direction, depends on which axis you're rotating it around, and the arc length, which is x dot squared plus y dot squared dt. So here, the height, r, if we're assuming we're revolving around it on the x-axis or the polar axis, the fancy name for polar coordinates, the height is r sine theta, because this is that. So our polar integral is 2 pi, that's the same, because we're still summing up lots of little circumferences of circles thickened up by the arc length, is r sine of theta. Oh, sorry, there's no square in there, my bad. The arc length over here, we just spent quite a long time finding that out, is square root of r squared plus r prime squared, and we can just slap a d theta onto the end of that and integrate it from theta 1 to theta 2, and there you have it. That will give the surface area of a polar function rotated around the x-axis.
There we go. If you have two cones and you slice them with a plane, you can get all sorts of different functions. And these are called conic sections, and we'll go more in depth with Cristobal.
Today we are going to find the equation of ellipse given this. First of all, what we can do is we can cross out the cross terms, which is just b of x or y. And we are left with ax squared plus cy squared plus dx plus ey plus f equals 0. What we want to do is clean it out a little bit, so in the near future we can complete the square. So we can do ax squared plus dx plus cy squared plus ey equals negative f. Now what we can do is we can move this ugly a and c out of the equation. We're left with ax squared plus d of x over a plus c of y squared plus e of y over c equals negative f. And now some more cleaning up. Just move this a and c to the other side, and we're left with 1 over c x squared plus dx over a and 1 over a y squared plus e to y over c equals negative f a of c. So I just took the coefficients out and moved to this side. So I have negative f over a of c. Make it a little nicer for when we complete the square. And so now we can finally complete the square. We will be left with 1 over c x plus d of 2a squared plus 1 over a of y plus e to 2c squared. And then by completing the square, we're left with all these extra terms, and I'm going to skip that and combine everything and add them all up, and we are left with negative 4 ac of f plus d squared of c plus a of e squared all over 4a squared c squared. Okay. And since it's an equation of ellipse, we want to have this side equal to 1. And by doing that, we can divide everything by this beautiful term to everything else. And now I'll just rewrite it. Okay. X plus d 2a squared all over c not yet negative 4 ACF plus D squared C plus A of E squared all over 4A squared C squared. Plus Y plus E over 2C squared over A negative 4A CF plus D squared C plus AE squared all over equals 1. I have rewrote the whole equation again, but this time I replaced negative D over 2A with H and E over 2C with K. Negative E. And so now, in order for us to get this in the ellipse friendly form, we have to square root it. We can square root it and then also square it. So the square root and the square cancel out, but we can just replace it at the end. But here we go. X minus H squared all over 1 over 2A square root negative 4 ACF plus D squared plus C plus AE squared all over 4A squared C squared plus Y minus K squared all over 1 over 2C square root of negative 4A C F plus D squared C plus A E squared all over 4A squared C squared. And we square in order for what we did to cancel right out. And if we look at this, we can just see that all this beautiful equation on the bottom is just a constant, and we can replace this with a letter. And I'm going to choose this to be A, little a, and this as little b. And we are left with x minus h squared all over a squared plus y minus a k. We're left with y minus k squared all over b squared equals 1. And that is our equation of an ellipse.
Thank you, Cristobal. Now we'll be exploring a new type of coordinate system called polar coordinates, where instead of y depending on x, r depends on theta. Here's Glennis with more details.
For this part, we're doing we're drawing the cardioid, and we're learning how to do that. So it comes from two basic equations. You start with either r equals a plus b sine of theta, or r equals a plus b cosine of theta. And the main difference between those is the orientation, so it depends which way the top and bottom are. If it's horizontal, it'll be cosine. If it's vertical, it'll be sine. And so you basically just plot the points and you draw it out. So starting with the equation, r equals 3 plus sine of theta. What you do is you get something like this, and you choose the points 0, pi over 2, pi, and 3 pi over 2. So you plug each one of those into the equation, and what you end up with is 3, 4, 3, and 2. And to plot it, you'd basically just plot it. So for 0, it would be 3, so it's right here. For pi over 2, it's 4, so it's here. And for pi, it's 3, so here. And 3 pi over 2 is 2, so right here. And then you draw it out, and what you'd end up with is something like this, which looks like an upside down heart. And that's basically how you graph a cardioid. Alright, so the rose is represented by the equation r equals 2a cosine of theta. And cosine of theta. The n is important because based on the n, it defines the number of leaves that you have on the rose. So one good way of telling how many leaves are on the rose is if it's odd, the number of petals is equal to n, and if it's even, the number of petals is equal to 2n. So this is odd, this is even. And if you want to know how far apart the petals are, all you have to do is you have to say, okay, so if it's even, it would be 360 degrees divided by 2n, and that would give you the distance between the petals. And same thing for odd, really, except it's n instead of 3n, so it'd be 360 degrees divided by n equals d petals odd. Okay, so that's just a basic overview. But an example of that would be the equation r equals cosine of 3 theta. Alright, so you can probably tell we skipped forward a little bit. So I drew you out an equation, r equals cosine of 3 theta, and to figure out why I chose the angles I did, you do what we learned from the last part. The angle between is equal to 360 over n. So you get angle between equals 120 degrees, which is equal to 2 pi over 3, and then you add that, so it's 2 pi, or 4 pi over 3, and then you have 2 pi, which is also equal to 0. So for this one, you'll get pretty much the same things. You'll get, you'll get all the same answers. We just need the angles. So for this one, it's just 1, 1, 1, and 1. And you draw it out. So the hardest part is probably figuring out the angle on the graph. So it'll be something like this. Okay, this is 1, 1. Okay, so you'll do that. Oops. Can't draw, you can probably tell. But it'll look something like this. Some of you can probably do it in one motion, but that's how it looks. Just like a rose. This is a graph for a lemniscate. You'll notice that it's very similar to the graph of a rose, but the main difference is that petals, the vertical petals, are actually imaginary because of the r squared. So if you drew it out, it would be something like this. But you don't really even have to draw it out. The difference between the cosine lemniscate and the sine lemniscate is that the sine is actually rotated by 45 degrees. So instead of it being on the x-axis, it would be at pi over 2 and 3 pi over 2. So it would be something like that. Also, we have the spiral. They're represented by one of two equations, r equals theta, or r equals 1 over theta. The main difference is where it starts and where it goes from there. So for r equals theta, it would start at the origin, and it would go, it would be getting bigger. And for r equals 1 over theta, it's the opposite. So it would be getting smaller. Pretty simple.
Thank you, Glynis. Now we'll be talking about by far the most interesting functions in chapter 10, cycloids. Cycloids are the paths traced by a point on a circle as it rotates along either a flat surface or, even more interestingly, the surface of another circle. Here's Jesse with the details.
So today I'm gonna prove the parametric equation for a standard cycloid. And in this picture we got this angle PCQ, that's angle theta. And first let's figure out xt. In this case, xt is actually, this is x. So that's OT minus PQ. And OT equals arc length PT. And PQ, we just leave it there. And from this triangle, we can see PQ actually is equals to B sine theta, which, by the way, PC represents B and CT represent A. So we got arc length PT minus B sine theta, and arc length PT is A theta. A, by the way, is the radius minus B sine theta. So yeah, we proved XC already. Next, we're gonna prove YT. YT in this case is this line, that's YT. And that's CT minus CQ, right? CT minus CQ. And we got CT, that's A, right? And CQ in this triangle is B cosine theta. And we prove YT. Right now I'm gonna explain the parametric equation for hypocycloid, which is here. It's kind of similar to the epicycloid. First, we try to figure out x theta. So by comparing these two equations, we notice there are only a few differences, like the sign here and here and here are different. So sine theta in this picture, x theta in this picture is O1Q plus SP. O1Q plus XP. And O1Q here is in this triangle, O1, O2Q, this triangle. And this, let me explain, this line is big R, and this small line here is the small r, of the radius of the small circle. So O1, O2, in this case, is big R minus small r. So big R minus small r times, in this case, is cosine theta. So we got this part. And next, we try to figure out SP. SP. So SP is in this small triangle, O2SP. And this angle here is theta, this angle, which is the same as this angle. It's also theta. And the angle MO2P, MO2P, that's alpha. So that makes this beta equals to alpha minus theta. And we know this angle is also beta because these two lines are parallel. So SP equals to small radius r times cosine beta, which is alpha minus theta. Okay. So same, we try to figure out alpha. And we know the arc length MN and the arc length MP are the same. Where is the arc length MN equals arc length MP. And arc length MN equals big R times this theta. And arc length MP here equals small r times this angle, which is alpha. So the same, we got alpha equals r theta divided by small r. And we plug back in here and also added the first part. We got we got this result for x theta. Now we try to figure out y theta. Y theta in this picture is this line, which is O2Q minus O2S. That's y theta. And O2Q is also in this triangle. O2, O1Q, which is R times sine theta minus O2 as is in this small triangle, which is small r times cosine, sine beta. Beta is the angle here. And we already got beta is alpha minus theta, and we already got alpha is big R times theta over small r. We plug in back. Anyway, we got the equation here. Okay, now let's try to figure out y beta. Since we got alpha equals big R theta over small r earlier, so we plug in the equation we got earlier for r theta, which is big R plus small r times sine theta minus small r sine theta plus alpha. We plug in here, and we got big R plus small r times sine theta minus r sine theta plus r theta over r. And it is the same thing as this, which is big R plus small r times theta over small r. And then finally we got big R times small r times, big R plus small r times sine theta minus r sine big R times big R plus small r divided by small r times theta.
Thank you, Jesse. So this about wraps up our discussion of chapter 10. Now, it may seem like all of these functions in your head are just going to be impossible to remember, but
nothing is impossible. You should get to the point where anyone else would quit, and you're not going to stop there. No, what are you waiting for? Do it!